The Big Bang Illustrated Timeline. The universe came into being 13.8 billion years ago. Planck Epoch. T equals 0 to 10 to the power minus 43 seconds. The time between 0 and 10 to the power minus 43 seconds after the Big Bang event is known as the Planck Epoch. Our universe is compressed into an unimaginably small volume of space and begins as an infinitely hot dense fireball. Our inability to describe gravity at the beginning of the universe. There are four fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Let's focus on gravity and how general relativity and quantum theory, our two most successful theories in physics, describes the force. General relativity is our modern theory of gravity. It describes a space-time continuum as the fabric of the cosmos. Space-time incorporates the three dimensions of space: up and down, left and right, and back and forth, and the fourth dimension of time. Matter and energy can warp space-time, and this gives rise to the phenomena of gravity. At the dawn of our universe, the density of energy in the hot fireball is infinite, and thus the curvature of space-time is infinite. Describing space-time as infinite does not help us understand what is happening during that period, and at this point, all our known laws of physics have broken down. This state of affairs is described as singularity. We need an alternative way of describing how gravity behaves at such a small scale, and the logical step is to look to quantum theory, which successfully describes the behavior of elementary particles and the other three fundamental forces at the smallest of scales. However, when quantum theory attempts to describe gravity, the math breaks down because there are infinite variables that it can't account for. As both general relativity and quantum theory stop making sense in the Planck Epoch, little can be known about this period. Quantum foam. It is hypothesized that in the Planck Epoch, space-time is extremely turbulent and warped, giving it a foamy character. The space-time foam is also known as quantum foam. Within this high-density environment, microquantum black holes and wormholes can appear and disappear, and a quantum fluctuation can give rise to an entire universe such as ours. Quantum fluctuations is the term used to describe temporary changes in the amount of energy in a point in space. These quantum fluctuations allow the creation of virtual particles. Virtual particles are particle and antiparticle pairs that are created out of nothing and disappear back into nothingness. In quantum mechanics, a principle known as Heisenberg's uncertainty principle places a limit on the time that a quantum fluctuation can persist. The greater the energy of the fluctuation, the shorter the time that it may last. So if the proposition is that one such quantum fluctuation led to the birth of our universe, how can our universe have persisted for such an extended length of time? Well, in theory, if the total net energy of our universe is exactly zero, it could exist for an indefinite period of time without violating the Heisenberg's uncertainty principle. The description of how a quantum fluctuation within the quantum foam can create a universe is a potential description of the birth of our own universe. Unified field theory. During the Planck Epoch, the unified field theory proposes that all the forces are unified as one fundamental force, supergravity. Our universe bursts into existence with the sudden and rapid stretching of space everywhere. Grand Unification Epoch. T equals 10 to the power minus 43 seconds to 10 to the power minus 36 seconds. Space stretches and cools, and as it crosses a transition temperature, gravity separates from the other forces. In physics, the Grand Unified Theory describes how at this high energy state, electromagnetism the strong nuclear force and the weak nuclear force act as one single force, the grand unified force. During this epoch, the earliest elementary particles and antiparticles are created. Inflationary epoch. T equals 10 to the power minus 36 seconds to roughly 10 to the power minus 32 seconds. As space continues to stretch and cool, it crosses another transition temperature, and the strong force separates from the electroweak force. This separation triggers a period of exponential faster than the speed of light stretching of space known as inflation. Einstein's theory of relativity says that nothing can move faster than the speed of light in space, but that does not preclude space itself from stretching faster than the speed of light. During inflation, a repulsive form of gravity causes the space in the universe to stretch at an exponential rate, and the universe doubles in size at least 100 times, going from the size of a billionth of a proton to the size of a grapefruit. Inflation ends when the repulsive energy decays into ordinary matter and energy, at which point ordinary Big Bang expansion takes over. What is the observable universe? The observable universe, as the name indicates, is a universe that we can observe from Earth. That is, light from the contents of the observable universe has had time to reach our instruments on Earth. Assuming that the universe is the same in all directions, the distance to the edge of the observable universe is the same in every direction. So the shape of our observable universe is a spherical ball with the observer at its center. The age of the observable universe is approximately 13.8 billion years. This number has been arrived at using two methods. 1. Measuring how fast the universe is stretching and working backwards. And 2. Analyzing the age of the oldest star clusters in our Milky Way. Later in the video, we will discuss how the first light was only able to travel across the universe after 380,000 years passed from the Big Bang event. But for now, let's focus on light having had approximately 13.8 billion years to reach the observer at the center of the observable universe. Space continued to stretch while the light traveled the 13.8 billion years to us, and the region of space from where that light originated is now 46.5 billion light years away from the observer. Therefore, the radius of the observable universe is 46.5 billion light years, and the diameter of the observable universe is 93 billion light years across. The circumference of our known observable universe is called the particle horizon. The particle horizon is not to be confused with the cosmic event horizon. The cosmic event horizon is the region of the universe from beyond which light emitted today can never reach us, because the space in between is stretching faster than the speed of light. The cosmic event horizon is around 16 billion light years away from us. The cosmic microwave background radiation. In 1964, the cosmic microwave background radiation, otherwise known as the CMB, was discovered. This radiation is the first light that traveled the 13.8 billion years to our instruments. As the photons traveled that distance, their wavelengths stretched, transforming the photons into microwave radiation. The CMB reveals a very uniform universe. The temperature of space is 2.7 Kelvin, and the slight variations of temperature that can be seen in the CMB differ by a factor of only 1 in 100,000. The differences in temperature reflected in the microwave radiation is a result of how matter and energy were distributed when the photons began their journey. That variation in distribution is theorized to be a result of minute random quantum fluctuations in the structure of the universe that were present at the moment when inflation started. Inflation amplified these fluctuations to cosmologically large scales, and so although the universe is seen to be incredibly uniform, it is not perfectly uniform. Over time, gravitational pull in the denser regions coalesced matter and energy to form the large structures we observe in the universe today, the stars and galaxies. It's important to remember that the CMB reveals what the universe looked like 380,000 years after the Big Bang, and not what the edge of the observable universe looks like today. As our instruments collect light from the far reaches of our universe, we are looking back into the past. Or to think of it on a smaller scale, the sun that we see in our sky is always what the sun was like 8 minutes ago, because it takes 8 minutes for the light from our sun to reach us. So similarly, the universe that we observe in the CMB is the universe that existed 380,000 years after the Big Bang. With the discovery of gravitational waves, it may be possible in the future to use gravitational signals to look further back in time. Inflation explains the uniformity of space and the flatness of the universe. The theory of inflation explains two properties of our observable universe. 1. The uniformity of space, and 2. The apparent flatness of the universe. At the largest of scales, the observable universe displays an extraordinary level of uniformity. There are, of course, distinct structures in space, such as galaxies and stars. However, from a distance far enough away, all of space seems to look the same from all directions, similar to how sand in a desert will appear uniformly distributed if observed from a plane flying high up enough in the sky. The theory of inflation allows the contents of the baby universe sufficient time to interact and come to a uniform density of energy and temperature before the rapid expansion occurred. It is that uniformity which is the present uniformity of space we observe today. Without inflation, the Big Bang model would not have given the baby universe enough time to reach uniformity in this way. Inflation also explains the flatness of our observable universe. General relativity describes how mass and energy can curve spacetime, and accordingly, the mass and energy of the universe can also curve spacetime. There are 3 possible curvatures the universe could have. 1. Positive curvature, 2. Negative curvature, or 3. No curvature at all, i.e. be flat. The critical energy density of the universe is the mass and energy contained per unit volume of space needed for a universe to be flat. That means the gravity produced by the mass and energy in the universe is such that it perfectly balances out the stretching of the universe. When the universe has critical density, it continues to stretch at a decreasing rate forever until infinite time has passed, whereupon the stretching will finally halt. But as we all know, infinity has no end. The density parameter. The density parameter, symbolized by the letter omega in the Greek alphabet, is used to determine what curvature the universe has. It is the average mass energy density of the universe divided by the critical energy density. If the density parameter is more than 1, there is positive curvature. If the density parameter is less than 1, there is negative curvature. And if the density parameter is exactly 1, i.e. the average mass energy density of the universe is the same as the critical energy density, then the universe is flat. For the universe to have positive curvature, there is enough mass energy density in the universe to produce gravity that will warp space-time enough to eventually overcome the stretching of space so that the universe will collapse back in on itself to form a closed universe. For the universe to have a negative curvature, there is not enough mass energy density to produce enough gravity that can halt the stretching of space, so the universe will be an open saddle-shaped universe which will continue to stretch forever at a decreasing rate. And we have already covered that in a flat universe, there is just enough mass energy density to produce gravity that perfectly balances out the stretching of the universe. What do we mean by a flat universe? When describing the universe as flat, it's not meant that it's flat in the same sense as a 2D shape is flat, but rather that the geometry of the universe is such that parallel lines will never cross, the angles of a triangle will always add up to 180 degrees, and the corners of cubes will always make right angles. In a closed universe, the angles of a triangle would add up to more than 180 degrees. In the open saddle-shaped universe, the angles of a triangle would add up to less than 180 degrees, and in the flat universe, as mentioned, the angles of a triangle would add up to exactly 180 degrees. Why do we think the universe is flat? We can calculate the density parameter using two methods, and both methods indicate that it is very close to 1, therefore suggesting that our universe is very close to being flat. The first method involves counting up all the mass energy in the universe, taking its average density and then dividing that average by the critical energy density. The second method involves drawing a massive imaginary triangle on the CMB and seeing if the angles of the triangle add up to 180 degrees. And indeed, it does. How inflation explains the flatness. But before we get too excited and state definitively that our universe is flat, we have to remember that the exponential stretching of space brought on by inflation drives the universe towards flatness, smoothing out the fabric of the universe. We can only measure the observable universe, which may be part of a much larger universe, which might not be flat. The analogy that is often used is how an ant sitting on the surface of a large inflating balloon would assume that the surface it is sitting on is flat, because that's how it would always appear to him from his tiny perspective. We may be that ant, and the universe is so massive that whatever we can measure will appear flat to us. What is space stretching into? We've spoken a lot about the stretching of space, but what exactly is space stretching into? Is this even a valid question? We know that space in our observable universe continues to stretch, so the observable universe grows larger in volume. Galaxies move away from each other, and the further two galaxies are from each other, the faster they move away from each other as there is more space stretching in between. The reason why galaxies themselves remain intact is because over shorter distances, the force of gravity can counteract the stretching of space. We are woven into the fabric of this universe, and therefore does it even make sense to ask what space stretches into, as we are unable to get out of the universe to find out. Say that the question does make sense. So far we've spoken only about our observable universe, but let's consider the global universe within which our observable universe lives. This global universe can either be finite or infinite. In our ant on a balloon scenario, the ant thinks he is on a flat surface, even though we can see he is on a 3D round surface. Similarly, we could be like that ant, living on a 3D surface, on a finite 4D hypersphere, which we can't detect. If the universe is infinite, however, the stretching of the universe in our universe adds to the infinite. This is similar to a number line. Numbers never end, no matter how far you count. New space-time real estate is being created all the time, and as there is nothing larger than infinity, space is not stretching into anything at all. Standard model of particle physics. When we think of an atom, we generally think of a nucleus made up of protons and neutrons surrounded by a cloud of electrons. If we look deeper into the heart of the nucleus, we find that the protons and neutrons are made up of more fundamental particles called quarks. Quarks, like electrons, are considered to be one of the elementary particles that make up our universe. The Standard Model categorizes all the elementary particles into either matter particles, otherwise known as fermions, or force carrier particles, otherwise known as gauge bosons. Fermions are divided into quarks and leptons. There are 6 quarks, up and down, charm and strange, top and bottom. There are 6 leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. Fermions create matter and the gauge bosons carry the forces between the matter particles. Gluons mediate the strong force between the quarks, holding them together within the protons and neutrons. Gluons also mediate the strong force between the protons and the neutrons, holding them together within the nucleus of the atom. Photons are particles of light which carry the electromagnetic force that holds the electrons in atoms. W and Z bosons carry the weak nuclear force, which is involved in some forms of radioactivity and also plays a role in how the stars burn. And finally, the Higgs boson is the corresponding carrier particle of the Higgs field, which is a quantum field that permeates all of space. Particle interactions with the Higgs field impart particles with their mass, and the Higgs boson is the local excitation of the Higgs field. The elementary particles created during the grand unification epoch exist as a hot, dense quark-gluon plasma that inflation distributes thinly across the universe. Electroweak Epoch, T equals 10 to the power minus 32 seconds to 10 to the power minus 12 seconds. As the strong force separates from the electroweak force, particle interactions create a large number of exotic and theoretical particles with unusual properties. An example of such a particle is the tachyon, a theoretical particle that travels faster than the speed of light. Electroweak symmetry breaking and the Quark epoch, T equals 10 to the power minus 12 seconds to 10 to the power minus 6 seconds. The Higgs field causes electroweak symmetry to break, resulting in the electromagnetic force and the weak force manifesting themselves differently. The Higgs field also confers mass to fundamental particles which were formerly massless at higher energies. As the universe cools to below 10 quadrillion degrees, quarks, electrons, and neutrinos, along with their antiparticles, form in large numbers. The 4 fundamental forces assume their present forms. During this epoch, a process known as baryogenesis creates an asymmetry in the creation of quarks and antiquarks, which results in slightly more quarks being produced. There is an extra quark created for every billion quark-antiquark pair. When quarks and antiquarks make contact, they annihilate each other to produce energy, and the surplus quarks will go on to form all the matter that we see in our universe. Hadron Epoch, from T equals 10 to the power minus 6 seconds to 1 second. As the temperature of the universe cools to 1 trillion degrees, the quarks combine to create protons and neutrons. Composite particles made up of quarks such as protons and neutrons are known as hadrons. In the extreme conditions of the Hadron Epoch, electrons can fuse with protons to form neutrons, giving off neutrinos. These neutrinos are able to travel freely through space at or nearly at the speed of light. These neutrinos make up the cosmic neutrino background of the universe. Like the CMB, the cosmic neutrino background radiation is a relic of the Big Bang, but unlike the CMB, we may never be able to observe this background radiation, as neutrinos interact very weakly with matter and are incredibly difficult to detect. The CMB is the picture of the universe when it was 380,000 years old, as that is when the first light began traveling toward the observer, whereas the cosmic neutrino background makes up the picture of the universe when it was only 1 second old. During this epoch, some neutrons and neutrinos also recombine to form new proton-electron pairs. Random combining and recombining is commonplace during this epoch. Lepton Epoch, from 1 second to 3 minutes. At the end of the Hadron Epoch, the majority of hadrons and antihadrons annihilate each other. Leptons and antileptons now dominate. Electrons come into contact with their antiparticles, positrons, to create energy in the form of photons, and photons collide with each other to form electrons and positrons. 10 seconds after the Big Bang, the temperature of the universe falls to the point at which new lepton-antilepton pairs are no longer created, and most leptons and antileptons are eliminated in annihilations, leaving a small excess of leptons. Nucleosynthesis, from 3 minutes to 20 minutes. The temperature of the universe falls to 1 billion degrees, and for the first time, atomic nuclei can begin to form. Protons and neutrons combine through nuclear fusion to form the nuclei of the simple elements of hydrogen, helium, and lithium. After about 20 minutes, the temperature and density of the universe has fallen to a point where nuclear fusion is no longer possible. Photon Epoch, from 3 minutes to 240,000 years. The universe is filled with a hot, opaque soup of atomic nuclei and electrons. The photons left over from the lepton-antilepton annihilations from the lepton era are scattered by these nuclei and electrons, so visible light cannot move freely. Recombination and Decoupling, from 240,000 years to 380,000 years. As the universe cools, free-roving electrons are captured by the atomic nuclei to form electrically neutral atoms via a process known as recombination. As a consequence, the photons in the universe are finally able to travel freely, and this event is known as decoupling. For the first time, the universe has become transparent to light, i.e. allows photons to travel freely through it, and these released photons are the ones that make up the CMB. By the end of this period, the universe is filled with a fog made up of 75% hydrogen atoms, 25% helium atoms, and just traces of lithium atoms. The Dark Ages, from 380,000 years to 150 million years. The period between the formation of the first atoms and the first stars are referred to as the Dark Ages, even though photons were present at this time. The Dark Ages are so called because there were no sources of illumination, i.e. no stars existed during this time. In this period, cold dark matter dominated the universe. Cold dark matter is a hypothetical form of matter that we currently don't know much about. What we do know is that its gravitational pull is required in addition to the gravitational pull of ordinary matter for stars and galaxies to move in the universe the way that they do. It is estimated that in the universe, for every kilogram of ordinary matter, there exists 5.5 kilograms of dark matter. In the fog of the universe, some of the hydrogen atoms collide into each other, emitting a very low energy photon with an initial wavelength of 21 centimeters. To find out more about the Dark Ages, scientists are on the hunt for these photons, which will have been transformed into radio signals as their wavelengths stretched to meters during their journey across the universe for the 13.8 billion years. Reionization, 150 million years to 1 billion years. Over time, gravity pulls matter together to create the first quasars via gravitational collapse. The UV radiation emitted by these quasars stripped the hydrogen gas atoms of their electrons, creating an ionized plasma. This process means that the gaseous fog is lifted around the quasars, and as a result, transparent bubbles form within the universe. Part of the aim of 21 centimeter astrophysics is to uncover how the transparent bubbles developed over time, therefore giving scientists more of an insight into what happened during the Dark Ages and how structures began to be formed within the universe. Star and galaxy formation, 300 million years to 500 million years onwards. Over time, pockets of gas are pulled together by gravity to become more and more dense. These clouds begin to collapse under the weight of their own gravity, with temperatures soaring to a point where nuclear fusion is triggered and the first stars are born. The stars act as furnaces, forging heavier elements from the lighter elements they are made of. The first stars were 100 times more massive than our Sun, 20 times hotter, 10 times more luminous, and they shone ultraviolet blue. These first-generation stars only lived for a few million years, and once they burned through their fuel, they died in a hypernova, spewing out an enriched cloud of elements. Then a process of stellar recycling occurred. Gravitational attraction pulled the debris of the previous generation of stars together until a new star was created, which then went on to create heavier and heavier elements. In this way, every subsequent generation of star created a richer composition of heavier elements than the previous generation. We are often said to be made of star stuff, and it is because the elements that make us have been forged within the guts of these stars. Gravitational attraction creates not only stars, but also the other structures we see in the night sky. Galaxies, groups of galaxies, clusters of galaxies, and superclusters of galaxies. Solar system formation 8.5 billion years to 9 billion years. Our Sun is a 1000th generation star, and matter coalesced around it to form the planets, asteroids, and comets of our solar system. Present day, 13.8 billion years after the Big Bang event. Stars continue to die and be created, and the universe continues to stretch. In fact, the universe is stretching at an accelerating rate, owing to a mysterious form of energy called dark energy. Like dark matter, dark energy is shrouded in mystery, and many predict that the physics of the future will be focused on trying to learn more about the darkness in our universe. We have now come to the end of our journey, having worked our way through the entire evolution of the universe as described by the Big Bang Theory. Please note that the timings are approximations, and some events mentioned in the different epochs did overlap. If you like my content and want to help me make more science and educational videos for YouTube, please consider becoming a supporter of London City Girl Knowledge on Patreon. Patreon is a crowdfunding platform where you can support your favorite online creators by giving them a small sum of money each month. In return, you will get rewards such as graphics and wallpapers for your phone and computer, educational cheat sheets which you can print off and keep, as well as ebooks on a range of educational topics. As always, I hope you enjoyed this video, and please subscribe to London City Girl to show your support.